GPU smoke simulation on compressed DCT space. In order to realize a high-quality simulation, a high-resolution simulation is required. Unfortunately, high-resolution simulations are very expensive. GPU simulation is one solution to this problem. However, memory resources of GPU are often limited. This makes it hard to simulate large-scale simulations on GPU. For example, suppose that a GPU only has 6 GB of memory while a target simulation requires 8 GB of memory. In this scenario, we cannot run the simulation due to the lack of memory. We address this problem by introducing a novel DCT compression. Before we start our simulation on GPU, we perform a pre-processing. This includes pre-computing DCT basis functions and computing initial conditions for density and velocity field. First, we partition the whole simulation domain into square blocks of 8x8x8. Second, data in each block are transformed into DCT space. At this time, we only carry 1/8 coefficients, so our method requires only 1/8 data compared to a full simulation. After that, these data are transferred to the global memory on GPU. Next, we enter simulation loop. Our simulation loop consists of following 4 steps. First step is to identify the maximal number of blocks that can uncompress within the shared memory on GPU. This process determines the peak of our memory consumption during simulation. Next, we focus on each block for further calculation. We uncompress data in each block onto shared memory. Using data on shared memory, physical quantities are updated as a regular smoke simulation. This includes velocity advection and pressure solver calculations. After updating, these data are compressed back to DCT space. We performed the processes on a set of blocks on the shared memory at the same time. When this is done, our simulation moves on to the next set of blocks and continue to calculate the same processes. Overall, our contribution is summarized as follows. First, DCT-based smoke simulation on the GPU that runs an order of magnitude faster than the CPU implementation without DCT. Second, on-the-fly compression and expansion of DCT space. Third, reduce DCT basis functions that retain visual details and less memory consumption. Fourth, our method requires a small incremental effort to implement on top of an existing fluid simulation framework. We performed a series of numerical experiments as we show as follows. This example compares the 2D simulations. Different compression ratios are shown. This example illustrates the effect of our compression. It shows that our simulation provides a visually closer result to the original than that of half resolutions. This example compares 3D simulations.